In this video, you will learn about the dot product, an important vector operation. The dot product helps us find the angle between two vectors and the projection of a vector on a specific line. Additionally, the dot product is significant in various areas of multivariable calculus. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel.
Let's begin by defining the dot product. Definition of dot product. Given two vectors u and v, then the dot product of u and v is the real number scalar, given by the sum of the products of their corresponding components. Since this vector operation yields a scalar rather than a vector, it is also called the scalar product or inner product of the two vectors. Let's see how the dot product works. To compute the dot product, we multiply the corresponding components and add. After solving the a and b items, we can see that the dot product of two vectors is commutative. That is, u dot v is equal to v dot u. This is the first property of the dot product. Solving item C, we find the relationship between the magnitude of a vector and its dot product with itself. The dot product of a vector with itself is the magnitude squared of the vector. This is the second property of the dot product. Other properties can be proved by performing the definition of the dot product of two vectors. Let's explore how the dot product of two vectors relates to the cosine of the angle between them. Let's start by placing vectors u and v in the standard position and considering the vector u minus v. These three vectors form a triangle, as shown in the figure, with magnitudes indicated. Using the law of cosines, we can write an equation. By utilizing the properties of the dot product, we can rewrite the left side of this equation. Substituting this back into the law of cosines yields another formula. Physicists use this formula as the definition of the dot product, known as the geometric interpretation. If theta represents the angle between two non-zero vectors u and v, where theta is between 0 and pi, we obtain. We can solve the equation for the cosine of the angle. Find the measure of the angle in radians formed by vectors u and v. To calculate cosine of theta, we need to first determine the length of both u and v. Then we can find the dot product of u and v, which is obtained from item A. Finally, we insert all of these into the formula above. Let's see another example. Find the angle between the vectors u and v. Let's start by calculating the dot product of vectors u and v. Then we'll find the magnitudes of both vectors. Finally, we can determine the angle we are looking for. When the angle between 0 and pi radians satisfies cosine of theta equals 0, it means that theta equals pi over 2 radians, and this shows that the vectors u and v are perpendicular. Hence, by utilizing the dot product, we have an effective way of ascertaining if two vectors are orthogonal or not. We can state that two vectors u and v are orthogonal if and only if the dot product between them is 0. The terms orthogonal and perpendicular are synonymous and are used interchangeably, although we usually use orthogonal when dealing with vectors. The terms perpendicular, orthogonal, and normal are all commonly used to describe geometric objects that meet at right angles. Usually, we say that two vectors are orthogonal if they meet at right angles. We say that a vector is normal to a plane if they meet at right angles. And two planes are perpendicular if they meet at right angles.
When working with a non-zero vector in a two-dimensional space, you can determine its direction by measuring the angle in a counterclockwise direction from the positive x-axis to the vector. In space, it's easier to measure direction by examining the angles between the vector and the three unit vectors, I, j, and k. The direction angles of a non-zero vector v are defined as the angles alpha, beta, and gamma that vector v makes with the positive x, y, and z axes. These direction angles lead us to a definition for the direction cosines. The direction cosines of a vector v are the cosines of its three direction angles. To calculate the direction cosine, we substitute the vector u in the formula above with the unit vectors I, j, and k. The direction cosines are related to the components of vector v in the following way. Now we can find an interesting formula if we take the three direction cosines, square them, and add them. So the squares of the direction cosines, when added together, equal 1. It tells us that the vector is a unit vector, and this vector is also in the same direction as our vector v. So we have found a unit vector in the direction of our vector v, which says that the direction cosines of vector v are the components of the unit vector in the direction of vector v. And finally, we can write the vector v in terms of its direction cosines. We summarize these ideas as follows. Let's see how it works. Let's begin by finding the length of the vector to solve part A. To determine the direction cosine of the vector, we need to divide the corresponding coordinate of the vector by its length. Direction cosines are the cosines of the angles between the vector and the coordinate axis. To find the direction angles, we can make use of the inverse cosine function. The sum of the squares of the direction cosines is given by a specific formula, and it's worth noting that the square of the direction cosines always add up to 1. Finally, we can express vector v in terms of its direction cosines. Sometimes it can be useful to project one vector onto another. The dot product can also help find the direction of vector u along a non-zero vector v. To understand this, let's look at two vectors u and v, which have an angle theta between them. The vector projection of u onto v is achieved by dropping a perpendicular from u to the line through v, as shown in the figure. The vector projection of u onto v will be in the direction of v, and the length of the vector projection is called the scalar projection. To find the scalar projection, we can use the right triangle, the unknown angle theta between the two vectors, and the cosine ratio. The cosine of the angle theta equals the dot product of vector u and vector v divided by the length of vector u times the length of vector v. We can substitute and simplify to find the length of the vector projection, also known as scalar projection. To find the vector projection of u onto v, you can multiply the scalar projection by a unit vector pointing in the direction of vector v. Notice that the vector projection is the scalar projection times the unit vector in the direction of vector v. We summarize these ideas as follows. If vectors u and v are both non-zero, the vector projection and scalar projection of u onto v can be calculated using the following formulas. Moreover, it is evident from figure that if we subtract the vector projection of u onto v from u, then the resulting vector will be orthogonal to vector v. We call this the vector component of vector u orthogonal to vector v. This shows that any vector u can be represented as a sum of two vectors, one parallel to vector v and another perpendicular to vector v. Let's see how it works. To calculate the vector projection and scalar projection, we need to start by finding the dot product of vector u and vector v, the dot product of vector v with itself, and the magnitude of vector v, and then plug them into the formula provided. To determine the vector component of vector u that is orthogonal to vector v, we simply subtract the vector projection of u from u itself. The diagram illustrates this scenario.